Swayam Prabha. Digital India. Educated India.
In the last class we were discussing about hybrid rockets and we had listed out the advantages of hybrid rockets over both solids and liquids, and I had made a point at the end of it saying it looks all very rosy with hybrid rockets. Why is it that it has not ever been used? We will try to list out the disadvantages in today's class and also discuss about the current efforts to overcome some of these disadvantages. One of the major problems with hybrid rockets is the burn rate. If you look at what I had said in the previous class, that any polymer can be used, right, and if you use any polymer along with an oxidizer, the burn rates that are obtained are very, very low. Okay, something it is typically around 1 to 1.5 millimeters per second. So as a consequence, what you will have is, if it has very low burn rate, okay, there is a particular O by F you can use, right. So if you use that particular O by F, then the thrust delivered by this system will be, because the mass flow rate of fuel is what we are going to get with the solid fuel, then you need to add the oxidizer mass flow rate. Oxidizer mass flow rate cannot be very, very large, right, then the O by F changes and the temperatures or the ISP that you will get will be very low. So it has to be within the range that it gives the best ISP. So if we do that, then the thrust delivered by this system will be very low, which is probably one of the biggest drawbacks. The other disadvantage with hybrid rockets is, if you remember, I had said that we can write the expression for the burn rate for a hybrid rocket as R dot is equal to A GOX to the power n, where GOX is nothing but mass flow rate, mass flux of the oxidizer in the port, right. So even if we keep this same, if we keep this constant, right, it is possible to get the fuel mass flow rate as nothing but this is the velocity at which it is getting consumed. Let us say we have a cylindrical port, okay, then we need to multiply it by the area. So that is right. Now this GOX is nothing but, GOX we had seen earlier is nothing but m dot OX by right. So this is GOx, this is nothing but mass flux. So if we expand this portion, okay, this is the expression for fuel mass flow rate that we get. Now notice that there is a diameter in the numerator, there is a diameter in the denominator. Typically the values of n ranges between 0.7 to 0.8. Okay. Now what happens if we have that kind of n? You will have n to the power of, if we take square 0.8, it will be 1.6 in the denominator and in the numerator 1. So effectively what you will have is, if we consider something like then what we are going to get is m dot f is equal to right. So what we have is the mass flow rate of fuel varies inversely as diameter to the power of 0.6. So even if you hold the mass flow rate of oxidizer constant, the fuel mass flow rate keeps on changing, right. So m dot f will be a function of, so depending on the value of n you will have different powers here, okay. So what we can see is mass flow rate of the fuel is not a constant during operation, because the diameter keeps on changing and the mass flow rate of fuel will also keep on changing. So what does this do? If m dot f varies, even if you hold m dot ox constant, what it will do is it changes your O by f, right. So essentially O by f is not constant during operation. Now this has more serious consequences in terms of, if we look at what happens to the specific impulse as a function of O by f, okay. I will try to plot here for a couple of them. So typically you will know that it will have a maxima at some particular O by F. In liquids and solids, in solids this O by F is preset depending on the amount of oxidizer that you have. So you can operate it at that set O by F. In liquids you can use the valves to take it to the particular O by F that gives the best performance in terms of ISP, and then operate your liquid motor liquid engine at that point. But here unfortunately with O by F ISP will change, and this is for HTPB plus liquid oxygen. Okay. Now what we see here is that if the O by F varies, then the ISP will also vary, right. So if you are wanting to design a system wherein the thrust is maintained constant, even nominally maintaining constant is very difficult with a hybrid rocket, simply because the O by F changes during operation and then ISP will change, so therefore thrust will change. Okay. In addition to this, the mass flow rate is also changing, right. The mass flow rate of fuel, even if you hold the oxidizer, mass flow rate is changing, so therefore holding thrust constant during operation is very, very difficult. Now the other trouble with hybrids is people have done this, looked at okay, we are saying that the burn rates are very low, right. When we discuss solid rockets, we discuss this, that only the burn rate and burning surface area are under the designer's control once you choose a particular propellant type. So you can increase the burning surface area and therefore make up for the lower burn rate is what we talked about, right. So people have also considered that, that is but what happens is they have come up with this kind of a design, that is, instead of having just one port, let us say I have multiple ports, right. Instead of just having one port, all these are ports, that is, you are taking a sectional view, right. So, there are multiple ports here. But if we do this, yes, we might be able to increase the thrust, but what about volumetric loading of the propellant? That will go down, right. So, we had said in one of the advantages of hybrids over liquids that the volumetric loading of the propellant is much higher compared to liquids, but that is no longer possible, okay, if we go in for multiple ports. Also, if you look at it, as they burn further towards the end, this could lead to very serious problems regarding the integrity of the grain and other issues might come in. So, multiple port design, although looks feasible on the outside, it has various problems. So, therefore, this is something that is also not looked at. Now, we have kind of listed out some of the major drawbacks. In addition to this, if you look at hybrid rockets, the other outstanding problem is what happens to the burn rate from the head end to the nozzle end. So, if we take a hybrid rocket motor, let us consider only the fuel portion. Okay. Now, if you look at this, remember when we discussed about solid rockets, we talked about something called erosive burning, right, and we said that if you look at what is happening, the mass addition that is coming into the port is increasing from the head end to the nozzle end, right, and therefore, what happens to the boundary layer thickness? The boundary layer thickness continuously decreases, and as a consequence there is a higher burn rate observed at the nozzle end. This is a system that works on this principle. So, therefore, what you will normally observe is that the burning is not uniform from the head end to the nozzle end. This also leads to the other problem, that sliver losses. Remember we said sliver is unburnt propellant, right? So if you continue burning this motor, at some point there will be some propellant unleft burnt at the not burnt at the head end, whereas the propellant would have completely burnt near the nozzle end, and there is a point at which you will have to stop, because this would then affect the motor casing itself, right? So therefore as a consequence of this, the sliver loss is going to be high. Okay. Now this looks like as such looks a big list that of problems that we have discussed, which makes it very difficult for hybrid rockets to overcome. In addition to this, there is something known as problem of scaling. What do we mean by this? It's simply put, if you do a lab scale test and if you do an actual motor, remember when we talked about solid rockets, we can get a very good feel of how does the burn rate vary in a strand burner and then in a ballistic evaluation motor, and it has very good very close to what you will get with a large motor. There is going to be some difference, but it is not a very large difference. Now similarly, what happens in a hybrid rocket is that if you burn a very small motor on a lab scale, because those are experiments that you can do very frequently and it is less expensive to do them, what is its bearing to a large motor? Unfortunately in hybrids the scaling is not very good from what you get with a small motor to what you get with a large motor. So people have done this experiment at lab scale, and for HTPB plus LOX, if you do something like 50 mm outer diameter port and 12 mm starting diameter. Okay. This is the same propellant, oxidizer, same fuel, same. If you do with this, the burn rate law that people get is something like right. Now if they do with the same propellant on a larger scale motor, right, that is something like 75 mm starting dia and 280 mm outer dia, right, the burn rate law that they get is very different. Now this makes it even more difficult to have a realistic motor, because if you want to design a large scale motor, it looks like you have to do all the testing at the large scale itself. There is no way you can do a small scale testing, get some measurements done and then use them for the large scale, because the burn rate laws themselves are not valid for, are not being the same for small scale and large scale. Even the N is very different, right. So this is another major problem with hybrids. So because of these problems, hybrids have not been able to be of the technology of hybrids is not at such a level that it can be used in a launch vehicle. Now some of these problems have been there for a very long time, and people have been looking at trying to resolve this, okay. And there are various things that people have done to overcome some of this. We will discuss that briefly. Now the first problem that we discussed was with regards to burn rate of the propellant. One of the thoughts that people have come up with is, if you look at the O by F requirement for highest ISP, right. O by F requirement for highest ISP if we can shift it to a higher value of O by F, that is you choose a fuel and oxidizer combination such that it gives the best performance at, let us say, 6, okay. There is such a propellant combination possible. If you look at hydrogen peroxide and HTPB, the highest ISP is achieved somewhere around 6. What it would mean is, you need to push in more mass flow rate of oxidizer, which also would mean that the fuel mass flow rate will be higher, because the two are related. So that is one of the suggestions to overcome this problem of low burn rate. This is also not such a great idea, because if you look at the specific impulse overall, even if you take this specific impulse that you will get even with H2O2 systems will be somewhere around 3000 seconds, 300 seconds or 3000 Newton second per kg, which is not a very large value that will force the industry to take a very positive view of this, okay. So, in a sense this idea does not sell itself so much. Now, the second this thing was to use ultrafine aluminum powder. Or nano aluminum. Now, people have done these experiments. They have found that if you use nano aluminum, you can increase the burn rates to something like 4 times what you get. That is, the fuel burn rates can be of the order of 4 millimeters per second, which is probably very good, and you can make a very good or a very high thrust motor with this, simply because if you look at what we are only talking of fuel flow rates, right. In addition to this, if you have if you take the O by F into consideration, the oxidizer flow rate will also be there. So, the overall mass flow rate will be much higher, okay. But the flip side of this is, if you look at nano aluminum, the cost of it is very high, something like 50,000 rupees a kg, okay. So, this is why it is again there are also issues when you make a motor of a large scale. How do you cure it? Because the number of particles becomes much larger. If you are using micron and suddenly you go to a nano scale, you are reducing the particle size by 1000, right. As a consequence, the number of particles will increase. It will go as cube of this 1000. So, sometimes it is very difficult to get a good cured propellant with good mechanical properties if you go in for something like nano aluminum, okay. So, then what people have also looked at is something called a mixed oxidizer concept, okay. Instead of just having a fuel alone, instead of having just HTPB alone, if we add ammonium perchlorate to it, right. If you add too much of ammonium perchlorate, then it will become like a solid propellant, right. There is a percentage of ammonium perchlorate that you can add such that it does not burn on its own. It should not start burning on its own like a solid propellant. So, you can add a little bit of ammonium perchlorate so as to increase the burn rates. So, people have done this also. This is known to give burn rates of the order of 4 millimeters per second, which is very good to kind of make a solid hybrid rocket engine. But the flip side is you cannot use beyond some percentage. It has to be something less than something like 25%. If you use more than that, then one of the advantages that we talked about hybrids, that if you switch off the oxidizer supply, it will stop burning. That won't happen, okay. So, there is this is somewhere around the critical content of AP that you can use. Then people have also come up with something known as a swirling. If you inject the oxidizer in an axial fashion, right? Let's say this is the fuel block. Now, instead of injecting the oxidizer axially, that is, instead of this, if you are able to give it a swirl, right? There are two advantages that you will get. One is, if you look at the actual surface area that the oxidizer gets to see, right, that will be larger because it is taking a very helical path, right. So therefore the actual surface area that the oxidizer sees is much more than the apparent surface area, and in addition you are injecting the if you look at swirl flow, because the fluid tries to because of the swirling nature of the flow, the fluid tries to stick to the walls, right, it tries to go close to the walls. So the actual velocity profile, if you look at close to the wall, that will be very high, and that will lead to very high burn rates rather than if you inject it axially, because the flow, most of the if you look at the velocity profile for an axial flow, it will be something like this, right. So there is a larger fraction of the flow is along the center line, whereas if you swirl it, most of the flow will be close to the walls, and therefore the burn rates are going to be higher with a swirl flow, and this has been found true. So this can lead to high burn rates, okay. But on the flip side, you are injecting the oxidizer in a swirl flow. What happens to the exhaust? Exhaust will also have a swirl component, which could, if it is only one motor, it is fine, it does not have a problem. But if you have two motors, then you have to look at having the swirls in the opposite direction, and you are not too sure whether they will cancel each other out or it will introduce a moment on the entire vehicle, which could take the motor into, entire vehicle into a spin, which is something that you might not want. So therefore this is also not such a feasible solution. The other two solutions that people have come up with are one is wax that is used to make candles, if you can use that as a fuel, simply because wax has a very low melting point. Now because of this low melting point, what happens when you have a transverse flow is the wax that is in a molten state, right, when you have a flow there will be droplets of wax that will get entrained into the flow. So therefore the mass burn rate of the fuel will be much higher, and what they found in experiments is that if you have a wax and oxygen system, you can get burn rates of the order of 5 millimeters per second. Okay. But the flip side of this is, if you look at candle, or if you have ever used a crayon is basically wax. It is very, very brittle. The structural or the mechanical properties of wax is very poor, and therefore as such it does not it cannot be used. You have to tailor the mechanical properties with certain additives so as to improve its mechanical properties. So currently its mechanical properties is something that is a problem. There is also another solution that people have come up with. Just like you have ammonium perchlorate that can burn on its own, right? There are oxidizers that can burn on their own at certain conditions. Is it possible to have fuels that can also burn on their own, right? One such fuel is glycol azide polymer, or GAP. So the burn rates that you can get with this is very, very high. It also has the other problem, that is, even when you switch off the oxidizer flow rate, it will not quench because this can burn on its own. So what people have done come up with is, you add another polymer of similar density such that the overall thing does not burn on its own, but when you have oxidizer flow and when you ignite it, it will burn, right? But the polymer used for that is PEG, or polyethyl glycol, which has very similar densities. Now the trouble with this system is, firstly burn rates are lower because you have added up inert polymer. The other thing is again the costs that are associated with GAP. Remember, when we spoke about hybrids, we said cost of it is very low because you can virtually use any kind of polymer. You need not have a very special polymer, and therefore the cost can be much lower, but that takes away the advantage, because you are now going to use something like a very expensive, something of the order of again 50,000 rupees, or if I am not mistaken $50,000 or rupees, I am not too very sure, per kg, okay, which is very expensive. So even if you build a practical system, people will say, why use this when we have established systems? If you look at the ISP variation with oxidizer or the O by F ratio, what you can get with a hybrid system is something that you can get with kerosene LOX systems, okay. It is not very different, right. So in a sense, if you look at most countries, all of them have kerosene LOX engines. India is probably the only country that does not have a kerosene LOX engine. So most countries look at it as something that you need to do in addition to what you already have, but you will still end up getting the highest performance that you can get is something similar to what a kerosene LOX engine would give. Why do take all the trouble and do something that is not any better? So therefore you will find that most countries have not really bothered themselves with work on hybrids. But there is a silver lining to it, in that sense that there is something called as aluminum hydride. Now aluminum hydride is considered as something that has a higher storage of aluminum per unit volume, even if you store hydrogen on its own, right. The density of hydrogen that you will get is 70 kg per meter cube, but if you use aluminum hydride and the volumetric loading of hydrogen that you can get is much better than what you can get with liquid hydrogen. But the technology of this making this is a very what should I say, very explosive compound. It is very difficult to stabilize this. It is very reactive with air because of the hydrogen, and if you have oxygen it will tend to react and give rise to water. So it is a very unstable compound and very difficult to control it. Only the Russians till now have the technology of making this, but if this were available, then you can get over LOX kerosene. The ISPs that you get with this aluminum hydride being used is something like 25 to 45 seconds higher than that is, if you use in a hybrid this aluminum hydride and you make a engine out of it, the ISPs that you get with those are going to be higher than what you will get with LOX kerosene. So in some sense this is driving the research forward. That is, if you can get a system that has a much higher ISP than LOX kerosene engine, why not use it, right? There was one other drawback of hybrids that I missed out on, that is something to do with if you remember combustion efficiency, when we discussed with regards to liquid rockets and solid rockets, we expected a value of greater than 98%, right, which also indicates what is combustion efficiency. In a sense indicates how much of the stated ISP you will be able to achieve. If this is very poor, then the ISPs that you get will be much lower than what the theoretical calculations will give. Now in hybrid rockets, if you look at it, the oxidizer is injected here, right, and one needs to be careful here, because if the oxidizer does not mix with the fuel that is coming in, fuel is coming in like this, and it needs to mix with oxidizer that is going along this direction, right. If you look at this geometry, the oxidizer in the center finds it very difficult to mix with the fuel, okay. So some of it might just escape without mixing with the fuel. So as a consequence, the combustion efficiencies are quite low. So therefore, whatever ISPs that you get from theoretical calculations, only a fraction of it you can get. So there are efforts to ensure that this combustion efficiency is also higher. So as such, if you look at the hybrid rockets as a whole, there seems to be a whole lot of problems associated with it, which is why it has not been used till now. And in a sense, if you look at it a little differently, it also is an opportunity for doing research in that area, simply because it has very good features. If you can somehow tailor some of these problems, I mean if you can overcome these problems by tailoring the fuel or some other means, then you can have a system that can have very good ISP and also is very safe, which would be something that you would require if you are planning to have missions wherein men are on board some of these rockets. Safety becomes a very, very critical issue then, right. So for such missions it is probably a viable option, and therefore there is a lot of interest in this area. Thank you.